Hi, George Diamond here. Now today we're going to be looking at the natural logarithm function and integration. Now let me go and get my Panama Jack hat with me today. Let me go and take my hat off and we're ready to get started. So let me put this out of the way. All right, as I said, now in our textbook, this is section 5.2. Okay, this is the natural logarithm function and integration. So how to integrate and how does integration with natural log functions? How does this work with natural logs? Now, in our last video, we looked at how to find the derivative of natural logs. So let's just do a little bit of a review. Let's make sure we can find the derivative of natural log. So if you remember our rules, so when you take the derivative of natural log x, it gives us 1 over x. Right? When you take the derivative of natural log u, gives you u prime over u. So anytime you take the derivative of natural log, you're going to end up with a fraction in which the numerator is the derivative of the denominator. So natural log x, the denominator is x, the derivative of x is 1, so you end up with 1 over x. And that's true for any natural log. So you end up with u prime over u, and that's how we take the derivative of natural log. Now just a couple things, I went ahead and wrote these down. Two things you got to remember now about natural logs. Natural log e is 1, right? So when you see natural log e in an expression of some type, that's going to simplify the 1. And the reason is you've got natural log is base e. And if you remember, anytime the base and what would be the answer part of a natural log are the same, it's simplify to 1. And natural log 1 is 0. So natural log 1 is 0. Okay, so let's do a little example. Erase these. Now let's do a little example of derivative. Let's take the derivative of y equals natural log x times the square root of x squared plus 1. So do a little example. Now when you're taking the derivative of a natural log function, one thing you got to do is expand it. So if you look at my natural log here, natural log of x times this square root, we have to expand this before we can take the derivative. It makes it much easier. So as we expand this will expand as y equals natural log x plus, this is a multiplication, so when you expand a multiplication, you expand it as addition, so it'll be plus natural log quantity x squared plus 1 to the 1/2 power. So I'll go ahead and rewrite that square root with a rational exponent. Now the rational exponent we're going to bring down front using the power rule for logarithms. So natural log x plus 1/2 natural log x squared plus 1. And now once you get your logarithm expanded, now we're ready to take the derivative. So as I take the derivative, y prime is equal to, now the derivative of natural log x is 1 over x plus, now as you take the derivative here, it'll be 1/2 times x squared plus 1 on the bottom of your fraction, so x squared plus 1, erase this, so plus 1. The top of your fraction is going to be the derivative of the denominator, so the derivative of x squared is 2x. And what happens is the 2's cancel out, and the derivative is equal to 1 over x plus x over x squared plus 1. And that's your derivative. So I just want to start off with a little example of differentiation involving a natural log function like this, because now we're going to transition quickly into integration. So as you look at integration now, with integration, the derivative of natural log x is 1 over x. Well, the antiderivative, or the indefinite integral of 1 over x is going to be the natural log absolute value of x plus c. Now, we have to put this absolute value on the x, because remember, natural log cannot be negative, so we got to prevent we can't use any values for x that would make that natural log negative. So we've got to put an absolute value here to make sure that comes out to be positive. So the domain of a natural log function, remember, is your answer part has to be greater than 0. It can't be equal to 0 or negative. So the antiderivative of u prime over u, okay, dx, is going to be the natural log absolute value of u, okay, plus c. So as you look at these are special fractions. So now one thing you notice now about our rule here for integration. This is the natural log rule for integration. You have within the integral, you will see in the numerator you have a fraction. Right? So some type of fraction. The derivative, so the derivative of the denominator will be in your numerator somewhere. And if you remember, anytime within an integrand, anytime you see the derivative of another part of the integrand or another factor of the integrand within the same integrand, we simplify this, or we take the antiderivative using u substitution. So when we evaluate definite integrals, or when we evaluate any kind of integral with these types of fractions that become natural logs, we're going to use a lot of u substitution with this type of problem. So just remember, the antiderivative of 1 over x is natural log absolute value of x plus c. And we'll be using this over and over again in some of our examples. The antiderivative of u prime over u is going to be the natural log absolute value of u plus c. All right, so let's get started. So we have a bunch of examples planned today. So a bunch of examples. Some of these examples are going to get kind of complex. So we'll look at a bunch of these. And hopefully by the time we get finished, you'll have a good idea as to how to find the how to integrate natural logs. Let's run through a couple examples. Erase this. There we go. Right. So number 1, let's start off with an easy example. Let's do 2 over x dx. Let's start with this here. Now 2 over x. Now first thing I want to do is just pull that 2 off. It'll be 2 integral 1 over x dx. All right. Now the antiderivative of 1 over x is natural log x. So we end up here with 2 natural log absolute value of x plus c. And that's it. That's all there is to it. So you can pull this 2 off. This is 1 over x. And then your integral, your answer here will be 2 times the natural log absolute value of x. Okay, let's look at another one. Okay, let's see if we have, what if we have this integral here. So erase this one. Number 2, what if we have the integral 1 over, so let's do 1 over 4x minus 1. Okay, dx. All right. Now this is a fraction, so anytime you're integrating a fraction like this, kind of look for, there's a good possibility that we could have a natural log relationship. So anytime if this is u and the numerator is u prime, right, then chances are that we could have a natural log relationship here. Now there's a couple ways to do this. There's a couple ways to do this particular problem. I'm going to use u substitution with each of these problems. Right, so each one. Because there are some problems, you have to use u substitution on. Now, I could do this problem really just by looking at it by observation, but I want you to kind of get in the habit of using u substitution with these types of problems. So somehow with this problem, I need to get 1 over u. Right, so what I'm going to do is, let's let the bottom of the fraction equal 4x minus 1. So 4x minus 1. So let's let u equal 4x minus 1. And let's do this, we know how to do u substitution. Let's take the derivative of both sides, so it gives us du equals 4 dx on the right-hand side, so take the derivative of both sides. And with the u substitution, we're going to solve this expression now for dx. So dividing both sides by 4 gives us 1/4 du equals dx. Now, let's go and make our substitutions now. We've got the integral 1 over u times. Now, instead of dx, we're going to substitute 1/4 du in. In for x. Now, we can pull the 1/4 out, so it becomes 1/4 integral 1 over u du. See the du there, all right? Now, we're ready to find our antiderivative. This has become 1/4 natural log absolute value of u plus our constant of integration. Now, the last thing we want to do here is rewrite our integral back in terms of x. So the original substitution, it says u is equal to 4x minus 1. Let's substitute this back in, it'll be 1/4 natural log absolute value of 4x minus 1 plus our constant of integration. All right. Now, one thing I want to point out, you may be thinking, why don't, this is 1/4 times this entire integral, why don't we multiply 1/4 to the c over here? Right, so technically you're multiplying 1/4 to your antiderivative. Well, if you do multiply 1/4, think of this in parentheses. If you did kind of use the distributive property here, you'd have 1/4 natural log absolute value of 4x minus 1 plus 1/4 c. Well, 1/4, now c is just a number. It can be any number. So 1/4 of any number is still any number. Right? So it's still c. So you don't have to multiply the 1/4 to your constant of integration out here. Just be 1/4 natural log absolute value 4x minus 1. Right, let's try another example. What if see, what about this here? Now, what if we had, what if, I'm going to do the same interval here. Okay, what if, instead of 1 over 4x minus 1, what if this had been 5 over 4x minus 1? Now, do it the same way. Let's say u equal 4x minus 1. We have du equals 4x, dx, 1 over dx, du, or 1 over 4x du. So du equals dx. So substituting back in will give us the integral 5 over u times 1 over 4x. So actually just 1/4, there's no x. The antiderivative of 4 is just 4, it'll be 1/4. Because we're not going to end up with an extra x here, so it'll be du. And this time we pull the 5/4 out front, it becomes 5/4 antiderivative 1 over u du. Right? So our answer is going to be 5/4 natural log absolute value of 4x minus 1. Okay, plus our constant of integration. So if you look at your answer, this is how it would make your answer differently if you had some number other than 1 here. Okay, let's try out another one. We're just running through a bunch of these as quickly as we can. And just kind of bear with me. Like I said, we have a bunch of examples that I want to go through. We've got several trig examples. We got a differential equation at the end that we're going to take a look at. So let's take a look at a couple more. Okay, take a look at, let's see, let's try problem number 4 here. Let's try this one. So number 4. This will be the integral 3x squared plus 1 over x cubed plus x dx. Okay, let's try this right here. Now I'm going to start off with that. Now I can, as I look at this problem now, I notice that the derivative of x cubed is 3x squared. The derivative of x is 1. So I can see that you've got the numerator is in fact the derivative of the denominator here. So I'm going to end up here. You already have u prime over u. Now I'm going to use u substitution on this. Let's say u equal x cubed plus x. Okay, take our derivative of both sides, and we have du equals 3x squared plus 1. Okay, dx, we have 1 over 3x squared plus 1 du equals dx. Okay, we're ready for our substitution now, so we end up here with 1 over, or actually we end up with 3x squared plus 1. So 3x squared plus 1 over u times 1 over 3x squared plus 1 du. Okay, these cancel out, and that gives us 1 over u du. All right, so once again, you see that 1 over u. All right, so you find your antiderivative now. This would be natural log absolute value of u plus c. Substitute back in, put this back in terms of x, will give us natural log absolute value x cubed plus x plus c. So fairly simple. You got your u substitution. Just go ahead and take the derivative of both sides. Set your substitution up, and then integrate. Now, let's try another one. And like I said, we're just doing a bunch of examples. All right. Well, let's try this problem right here. Let's try it. We'll do a little trig problem. What about this one? Number 5. Okay, what about the antiderivative of secant squared x over tangent x, dx. Now, by the way, I recognize the derivative of tangent is secant squared. So once again, the numerator is in fact the derivative of the denominator. So we'll let u equal tangent x. So du is equal to secant squared x dx. So we have 1 over secant squared x du equals dx. And let's go and set up for our substitution. Now we end up with the integral secant squared x over u times 1 over secant squared x du. Secant squared x's cancel out. That gives the integral 1 over u du. And there we go. That's where we want to be, because the antiderivative of 1 over u is natural log. So this will be the natural log absolute value of u plus c, or natural log absolute value of tangent x plus c. So this is going to be our antiderivative now. And as you look at this fraction, this is a special type of fraction where the numerator is the derivative of the denominator. So as you look at this, this is u prime. Okay, this is u. So this is definitely a natural log relationship here. All right, let's see. Let's try another example. So that's a little trig example. let's try, let's see, let's try this problem right here. Okay, let's try number 6. Okay, let's try the integral x plus 1 over 2x plus, or x squared plus 2x, okay, dx. Now let's get a fraction. Now watch for a natural log relationship. Now, as I look at the derivative of the denominator here, now the derivative of x squared is 2x, plus the derivative of 2x is 2. Now the numerator is x plus 1, all right? So you don't have the, as you look at the, comparing the numerator to the denominator here, the numerator should be the derivative of the denominator. But notice, if I factor 2 off, I can see x plus 1 in the derivative of the denominator here. So that's what we're looking at here. So we have a natural log relationship. So let's start it off. Let's let u equal x squared plus 2x. So x squared plus 2x. So du is equal to 2x plus 2. Okay, dx. And then 1 over 2x plus 2 du equals dx. And let's see, let's write this as 1 over 2 times x plus 1. Du equals dx. So I can see the x plus 1 there. So as we substitute back in, it gives x plus 1 over u times 1 over 2 times the quantity x plus 1, okay, du. Now the x plus 1's cancel out. We're going to pull the 1/2 out front. The 1/2 integral, 1 over u du. Now that's, once again, this is where we want to be now. I want to see that 1 over u. Okay, there's my natural log now. All right, so as we set this up, it's going to be 1/2 natural log absolute value of u plus c. And this is 1/2 natural log absolute value of x squared plus 2x plus c. And there's our answer now. So just use u substitution on it, and very quickly you can integrate, make sure you pull the 1/2 out in front of the integral, and then you can see the 1 over u. All right, let's try another one. All right, let's try. Right, now we've done some fairly easy problems. This is fairly straightforward u substitution. Okay, let's try a definite integral. All right, so let's try one of these. Are all indefinite integrals plus c. All right, so let's try a definite integral, area between the curve and the x-axis. So on number 7, okay, let's do a definite integral. So a definite integral. All right, so let's do the integral from, now we'll do from 0 to 3, okay, x over x squared plus 1 dx. Let's see if we can evaluate this definite integral now. So to start off, I know that the derivative of x squared is 2x. I can see the x in the numerator there, so this should work. So let's do a u substitution. Let's say u equal x squared plus 1. Du is going to equal 2x dx. Right, so 1 over 2x du equals dx. Now also we need to convert the upper and lower bounds from in terms of x in terms of u also. So let's go back to the original substitution here. This would be u of 3 equals 3 squared plus 1, which is 10. Right, so I'll look at my integral here. Okay, this will be 10. Okay, this substituting 0 in for x in the original substitution, so u sub 0. And it would be 0 squared plus 1, which is 1. All right, so our new upper and lower bound will be from 1 to 10. And this will be x over u times 1 over 2x du. Now you can see that x's will cancel out. And once again, the 1/2 we're going to pull out front, so it becomes 1/2 integral 1 to 10, 1 over u du. All right. Let's get our antiderivative now. So we end up here with 1/2 natural log, the absolute value u. Now there's no plus c, all right, this will be from 1 to 10. Okay, let me erase this over here. I'm going to need this a little bit more room. So now once you've got your antiderivative, all right, and get the substitute our upper bound minus our lower bound in for u now. So we'll have 1/2 natural log, absolute value of 10, or which is just 10, absolute value of 10 minus 1/2 natural log, absolute value of 1. All right, so the upper bound minus the lower bound, and this is 1/2 natural log 10. So 10 is positive 10, so we can drop the absolute value there. And this becomes, now remember we said natural log 1 is 0. We have 1/2 times 0, which is 0. All right, so our answer then is 1/2 natural log 10. Now if you got a calculator, you can punch it up on your calculator. You can see what the decimal answer would be. But this is just an example of a definite integral. You find your antiderivative, substitute the up. Now put the upper and lower bounds in terms of u also, and then go ahead and find your antiderivative, and then substitute the upper bound minus the lower bound. So this would be in parentheses here also. All right, now let's try another example. All right, so let's try this one here. All right, now, like I said, we kind of looked at some fairly easy problems. Just have to, if you know how to do u substitutions. These first 7 problems were really, really pretty easy. Okay, we're going to take a look at some that are a little bit harder now. All right, so let's take these natural log integrals can actually get fairly complicated, so fairly quickly. So let's look at let's try this problem right here. This will be number 8. Okay, let's do the antiderivative of x cubed minus 8x over x squared. Dx. Now, anytime I see a fraction, immediately I start looking for a natural log relationship. Okay, is the numerator the derivative of the denominator? No, it's not. The derivative of x squared is 2x, and the numerator's got x to the third, so it's not even close. But as a general rule, anytime you have a fraction like this with the denominator is just a single term. Whether you have a binomial divided by a monomial term like this, or a trinomial divided by a monomial. Okay, let's divide this x squared into each of these terms. We're going to break this type of integral up. This will be x cubed divided by x squared minus 8x over x squared dx. So I'm going to break that fraction up. Divide both terms in your numerator by x squared, and then simplify. So it becomes x cubed divided by x squared becomes x minus. So minus, and then here the x's will cancel. You end up here with 8 over x dx. Okay. See, now I'm going to look at this as 2 separate integrals. Right? So you kind of break this type of integral up. We've got the antiderivative of x dx minus, and we'll pull the 8 off of here, so it'll be 8 times 1 over x dx. Now, so think of it, if you want to, think of it as 2 separate integrals, right? And it can make the problem, as you focus on each part of your integrand here, it can maybe make it a little bit less complicated. Now, the antiderivative of x, this is exponent of 1, will be x squared over 2 minus. Now, the antiderivative of 1 over x, that's a natural log, right? So we end up here with 8 natural log absolute value of x plus our constant of integration, and we're done. Right? So it'd be x squared over 2. And x squared over 2 is the same thing as 1/2 x squared. So you can write it either way probably, but be able to recognize that those are the same. So it'd be 1/2 x squared minus 8 natural log absolute value of x plus our constant of integration. Okay. Now let's try another one. All right. Like I said, we're getting into. Make sure that we look at some of the more difficult problems, right? So far it's been fairly straightforward u substitution. Everything cancels pretty much. So let's try this right here. Let's be number 9. Okay, let's try the integral 2x squared plus 7x. So 2x squared plus 7x minus 3 divided by x minus 2 dx. My goodness. Now look at this problem, all right? And now right away, first thing you want to check for, do we already have a natural log relationship? Well, is the numerator the derivative of the denominator? Well, the derivative of x is 1, the derivative of 2 is 0. You look at the numerator, that's a trinomial, so we do not have a natural log relationship. So right now, u substitution would not help me. All right. Okay, also, in my denominator here, I have a binomial. So you don't want to break this up into 3 separate fractions. If the denominator is just a monomial term, Yes, go ahead and break it up, but this here won't help. Now, to do this problem, we have to use long division. Okay, we have to use long division to do this problem, to simplify it. Now, here's how the long division goes. We're going to take the, now, anytime you see a fraction like this in which the exponent or the power of the numerator is greater than the power of the denominator, we'll have to use long division. Or if the powers are the same, we're going to have to use long division. So or long division may work. Now, it may not work either, but there's a chance, a good chance that we could get a natural log relationship out of that type of problem. Now, with long division, we're going to take the x minus 2, and we're going to divide that into our numerator here. So this will be 2x squared to plus 7x minus 2. Okay, let's do this division. So hopefully you're up on your long division skills. So let's start off. Let's divide x into 2x squared. Now remember, when you divide the x's, you subtract your exponents. So it'll be 2 minus 1 will give us 2x here. I'm going to put the 2x over top of the 7x to kind of keep the factors of the same variables lined up there. Okay, that's going to be our quotient. Now, next thing you want to do after you divide, you got to take the 2x and you got to multiply it back to your binomial here. So both parts. 2x times x gives us 2x squared. 2x times negative 2 is negative 4x. Draws a line. Now, you remember in division now, after you multiply this first division here, your quotient, that part of your quotient back to your divisor, now we're going to subtract this expression from the dividend here. So let's put this in parentheses. Okay, we have to subtract now. Now, to subtract, I want to just distribute this negative to both of those, and we'll add them up. Now, 2x squared and negative 2x squared, those are going to add up to 0. 7x and 4x gives us 11x. And let's bring down the minus 2. Now, let's divide one more time. Now, we're going to do that same process again in long division. X will divide into 7x, or into 11x. Now, think about it. 11x over x, the x's cancels out, and it gives you positive 11. So x will divide into 11x plus 11 times. So let's put that up in our numerator there. Okay. Now we've got to multiply the 11 to both terms in our divisor. So we have to multiply the 11 to the x and the minus 2. So 11 times x gives us 11x. 11 times negative 2 is negative 22. All right. Now, so we're going to change the sign. So we have to subtract that now from our numerator here. Make this plus. That'll be negative. That'll become plus here. These add up to 0. Negative 2 plus 22. Actually, be 21, not 22. My bad. Make that change there. So it'll be 11 times 2, so times 2, actually it should be 3. Let me erase this here, there we go. It should be minus 3. So minus 3, here we go. So minus 3, this becomes 22, there we go. And I'm glad I finally caught that. Just got to be careful as you copy your problem down here. Now as you combine these now, negative 3 and 22 gives us 19. So we end up with a remainder of 19. So we can't continue with our division now. X won't go to 19. Now to write our quotient would be 2x plus 11. And then we're going to put our remainder back over our divisor. So plus 19 over 2x, or over x minus 2. All right. Now this is our quotient. After we divide x minus 2 into the numerator there, this is what we end up with. So I'm going to take this answer and I'm going to replace that big fraction up here. So this becomes 2x plus 11 plus 19 over x minus 2 dx. Now, this is the reason for the long division, right? So when you actually do the division, you end up with the quotient plus the remainder back over the divisor, right? Now, this is a lot easier to take the antiderivative of. Once again, think of this as 3 little integrals. We're going to integrate 2x dx plus the antiderivative 11 dx. Now, you don't have to do this. If you can go ahead and do it, find the antiderivative of each term the way it is, you can. Then plus, I'm going to pull the 19 off. It'll be 19 integral 1 over x minus 2 dx. Let me erase this. I don't need this anymore. Okay. Now let's go to integrate each of these terms. Now the antiderivative here would be 2 times x squared over 2. Now the 2's are going to cancel out. Okay, plus the antiderivative of 11 is 11x. You just add the variable, remember there. And then plus, this would be 19. Now the derivative of x is 1. So we have a natural log relationship there. It'd be natural log absolute value of x minus 2 plus our constant of integration. And our final answer, x squared plus 11x plus 19 natural log absolute value x minus 2 plus our constant of integration. So that's the reason for the long division. In the original form of our integrand, you could not integrate this until you divide the x minus 2 into that trinomial using long division. And you end up with, after you do your division, you've got your quotient plus your remainder back over your divisor. You can then, from there, you can see this with this fraction now, you have a definite natural log relationship. This is what it's going to simplify to. All right. Now, I did mention, right, that the problems are starting to get a little bit harder now. So we've done some of the easy stuff with just direct substitution. So we've done some of the easier stuff. Now we're doing some of the harder stuff. The long division, if you haven't seen long division in a year or so, it can be, you may need to kind of brush up on our long division skills. But let's try another one. Let's erase this. Okay. Let's see, let's try this problem right here. Okay, let's try let's be number 10. Let's do the integral 1 over x natural log x dx. Okay, what about this one? So 1 over x times natural log x. All right. Well, now let's see. Do we see the derivative, or do we see a part of the integrand here that is the derivative of another part? So let's see, what could we let u be equal to here? We're going to use u substitution. So what could we let u be equal to? So let me see. Let's do a little investigation here. Let's let u equal x. Let's see if this will work. It gives us du equals dx, which gives us 1 over u natural log x du. Now we're stuck with that natural log x. That won't work. What about, what if we were to let u equal, let's let u equal the denominator. Let's do x natural log x. Okay, what about this? Now to take the derivative, this will be du equals, now to take the derivative of x times natural log x, that's a product. So we have to use our product rule here. This will be x times, now the derivative of natural log x is 1 over x plus natural log x times 1. So you end up here with the x's cancel out. 1 plus natural log x dx. I don't like the look of that. I mean, you get up here with du equals this expression. So there's no way that's going to cancel out here in that fraction. So let's try, now we did the x and then x natural log x. Let's see if we can let u equal natural log x. Let's try this one. And sometimes when you're doing u substitution, it may take you 1 or 2 tries before you find something that will work. Now, as you take the derivative, du is equal to, now the derivative of natural log x is 1 over x dx. Now, I believe this is going to work. Actually, I notice that x over here in my integral, right? So let's multiply x to both sides. That's going to cancel out here. Let's multiply x here. So x du equals dx. So let's go and simplify. This will be 1 over x times u times x du. And the x's here are going to cancel out. And right away we notice we have 1 over u du. That's, once again, that's what we're looking for. That's what we're shooting for. The antiderivative of 1 over u is natural log absolute value u, okay, plus our constant of integration. And let's substitute the original, put this back in terms of x with our original substitution. This would be natural log absolute value of x, absolute value plus c. Well, look how weird that is. You have natural log absolute value, then natural log absolute value of x again, right? So kind of an odd looking answer here. Natural log of a natural log, kind of strange. But this is it. Right, so this is the only way really to integrate this type of fraction. Okay, let's try another one. Okay, let's take let's try a couple of trig integrals. We haven't looked at any trigonometry really hard at all, so let's try a trig integral. Okay, let's try, let's be number 11 here. Let's try this one. Let's find the antiderivative of tangent x dx. So antiderivative of tangent x dx. Well, first of all, there's no fraction, or is there? Remember that tangent x is equal to sine x over cosine x, right? So we're going to rewrite that. There's my fraction. So we're going to rewrite this as the integral sine x over cosine x dx. All right. Now, as soon as I do that, I recognize immediately that within the fraction, I know the derivative of sine is cosine, the derivative of cosine is negative sine, so I can see within that fraction, I can see the derivative of another part of the integral. So, for u substitution, I'm going to let u equal sine x. I'm sorry, not sine, but we'll do cosine x. We'll do the bottom of the denominator. So cosine x. So we end up with du equals. So du equals, let's do, now the derivative of cosine is negative sine, so it'll be negative sine x dx. And 1 over negative sine x du equals dx. So let's go make our substitution. So the integral sine x over cosine x over u. We're going to do our substitution here. So sine x over u times 1 over negative sine x dx. Now the sine x's will cancel out. Let's pull this negative out in front of the integral. And there we got it. Negative integral 1 over u du. Okay, so let's go and get our antiderivative now. This will be negative natural log absolute value u, okay, plus our constant of integration. Now let's put this back in terms of x, so substitute cosine x back in for u. So let's be negative natural log absolute value of cosine x plus our constant of integration. Okay, and if you'll notice now, so far in calculus, my classes, we have not looked at the antiderivative of tangent x. And the reason is you've got to use natural logs to find the antiderivative. So the antiderivative of tangent x is negative natural log cosine x plus c. Now, when we give us a new list of some of these trig antiderivatives, right? They involve natural logs. Now, if you had to integrate something like the antiderivative of cotangent x dx, well, you're going to do this the same way. Cotangent is cosine x over sine x dx. So we put it in fraction form, and then you can go ahead and you do this. You would do that the same way we did tangent x. All right, let's try. And by the way, this is going to give you the antiderivative of cotangent x. I'm not going to do it here in class. That may be one of your homework assignments or something like that, but you set it up the same way. Okay, let's try another one. Erase this. Okay, number 12. Okay, let's take another trig problem. Okay, how about secant x? What about the antiderivative of secant x dx? Right. Now, right away you recognize that secant x is equal to 1 over cosine x. Right, so let me see if we can set this up in 1 over cosine x dx. All right, and let's let u equal cosine x du is equal to, now there is cosine is negative sine, so it'll be negative sine x dx. And it gives 1 over negative sine x du equals dx. So substituting this back in now gives the integral 1 over u times negative sine x du. That's not going to work. There's no way we can get that negative sine x to cancel out. Even if we go back to the original substitution, there's nothing we can do there. Remember, u equals cosine x, so sometimes if you're stuck with an extra variable, right, you can go back to the original substitution. There's nothing we can do here. That's not going to work. So we're going to have to use something different to calculate or to determine the antiderivative of secant x. So that's not going to work. So right away, for most of us, we're going to try to make a fraction out of it, use u substitution. That's not going to work there. Now so let me show you what we're going to have to do here. I'm going to rewrite secant x by multiplying it by 1. Now, if you multiply something by 1, you don't change it. So that's what we're going to have to do here. Now, I know that the derivative of secant is secant squared. So here's what I'm going to do this. I'm going to rewrite this as the integral, okay, secant x times a fraction here. So secant x plus tangent x divided by secant x plus tangent x dx. So I'm going to multiply secant x by a fraction. So I'm going to make a fraction here. So I'm going to get my fraction. And if I can get that fraction, maybe I can get a natural log relationship. So I'm going to multiply secant x by secant x tangent x divided by itself. So when you secant plus tangent divided by secant plus tangent is 1. So let's multiply secant x to this now. Our integral becomes integral 1 over secant squared x plus secant x tangent x divided by secant x plus tangent x dx. Now, notice what we got. The derivative of secant is secant squared. The derivative of tangent is secant tangent. Right? So as you look at this, this becomes as you evaluate this integral now, this becomes the natural log, absolute value, secant x plus tangent x plus our constant of integration. And the antiderivative of secant x is natural log, absolute value secant x plus tangent x. That's how you get it. Now that was kind of tricky, but to get that, right away you want to write secant as 1 over cosine, but that does not work with secant. Now once again, another one of these trig integrals, in which we're going to have to memorize. Now we just did tangent a little while ago. Cotangent, we'll have to know this is another one. We have to be able to find the antiderivative of secant x. Now, you don't want to have to do this over and over again to get the antiderivative of secant x. You want to memorize this. Right? So put a little star next to this one. Okay, this we need to know, along with some of the other trig integrals. And when we get into class, will give us a list of each of these that we're going to need to have memorized. But that's one we're going to have to know. This is number 12. Let's try another one. All right, let's see. Let's try another trig problem. Let's try this one here. This is number 13. Okay, let's do the integral. Now, last time, earlier we'd kind of set up how to do cotangent x, but what about this here? What if we had cotangent of theta? Let's see. We'll do theta over 5 d theta. What about this type of problem? All right, so what about this type of problem? Now, if you remember now, cotangent x is equal to cosine x over sine x. So I need to get something like that, because that's going to give me a natural log relationship there. Right? Because once you rewrite this as a fraction, but to start off, though, I'm going to let u equal 1/5 theta. So I'm going to pull that 5 off and be 1/5 theta. Right? And as we find our antiderivative, or find our derivative rather, so du equals 1/5 d theta. So the derivative of 1/5 theta is just 1/5. Right? Now multiply both sides by 5. Multiply 5 here. So 5 du equals d theta. All right. So let's remove that that theta over 5 now. This becomes the cotangent x, or in this case cotangent u, times 5 du. Let's pull the 5 out front. So 5 integral cotangent u du. Right. Okay, now cotangent u, I'm going to rewrite that. All right. So this is, I'm going to get my fraction now. So remember, we're looking for the fraction. This will be 5 integral. This will be cosine u, sine u, du. Everything is still in terms of u. And now you can see that the derivative of sine is cosine. That's my natural log relationship here. So I have 5 natural log absolute value of sine u, okay, plus our constant of integration. And remember now, let's convert back in terms of theta. Right? This will be equal to 5 natural log absolute value of sine theta over 5, okay, plus our constant of integration. Okay, so that wasn't too bad. It wasn't too bad, but you got to start off. We want to get here with this particular problem with cotangent, we want to get it in fraction form as quickly as we can. So we'll start off with u substitution, that u equal the quantity inside our parentheses here. So that wasn't too bad. Okay, let's try another one. All right. Okay, let's erase this. There we go. Okay, let's try. So we did a trig problem. Okay, let's try a problem, because I said sometimes when we're using u substitution, we're stuck with an extra variable. So let's try a problem like that where, all the x's do not cancel out. So let's take a look at that type of problem, right? Because, with my students, when they get their assignment later on, they get their homework, they'll be seeing this type of problem. And these are the most difficult to do with u substitution. So let's see, this will be number 14. Okay, let's do the integral. 1 over 1 plus the square root of 3x. So 1 over 1 plus the square root of 3x dx. Let's try this problem here. Remember, we want to try to get 1 over u somehow, so let's start off. Let's let u equal the square root of 3x. So u equals 1 plus the square root of 3x. So instead of square root of 3x, I'm going to write this as the quantity 3x to the 1/2 power. So once again, let's convert it from radical form to rational exponent form so we can quickly take the derivative. Now, as we take our derivative, du is going to equal. Now, the derivative of 1 is 0. Now, as you take the derivative of 3x to the 1/2 power, you have to use the chain rule here. The outside part of the function is going to be the 1/2. Inside part is the 3x. So as you take your derivative, you bring the 1/2 down front. Leave the inside the way it is. Now you got to remember to subtract 1 from your exponent now. That becomes negative 1/2. So negative 1/2 times the derivative of the inside, which is 3. Okay, let's see if we can clean that up a little bit, make it a little bit easier. I've still got this radical over here. So du is going to equal. Now let's see, this right here is going to go to the bottom of our fraction with the 2. The 3 is going to go to the top. So now we've got 3 over 2 square root of 3x dx. So dx here. Okay. Let's see, now solving this for dx, I'm going to multiply by my reciprocal. So 2 square root of 3x over 3. Now these two are going to cancel out. Let's multiply this side over here by 2 square root of 3x over 3. So let's make our substitution now. So our integral becomes 1 over u times 2 square root of 3 over, so square root of 3x over 3 du. All right. Now, notice now, as you look at this problem here, we're stuck with x. So anytime and we have an extra x variable here that we can't cancel out. Now, I can pull the 2/3 out front, though, so it becomes 2/3 integral 1 over u times the square root of 3x du. So this is what we have. All right, now anytime you've got a variable, an extra x or an extra variable like this that you can't get to cancel out, always go back up to the original substitution. Because a lot of times the original substitution, we can eliminate this extra x here. So let's pull this down front. And this is u equals. So this is u equals 1 plus the square root of 3x. Now, I need to get rid of the 3x. So that means that u minus 1 equals the square root of 3x. That's how I'm going to get rid of it. U minus 1 is equal to 3x. So I can rewrite or substitute u minus 1 into our integrand for 3x. So it becomes 2/3 integral 1 over u times u minus 1 du. So this is what our integral becomes. Now, everything is now in terms of u, but we do have to simplify it a little bit. All right, so I've got 1 over u times the quantity u minus 1. So let's start off, let's go ahead and remove our parentheses. So let's multiply u minus 1 inside of our parentheses. So use our distributive property here. So bring the 2/3 down, so you get 2/3 integral. Now 1 over u times u, remember when you multiply here, 1 over u times u, the u's cancel, equals 1. So this becomes 1 minus 1 over u times 1 becomes 1 over u, integral du. Okay, now we're ready to find our antiderivative here. So erase this. I think I can erase this here too. So let me go ahead and bring this up. So I've got some extra room. So we have 2/3 integral 1 minus 1 over u. And it's become now 2/3. Now the antiderivative of 1 is u with respect to u, so it'll be u minus. The antiderivative of 1 over u, that's our natural log now. So this will be natural log absolute value of u, okay, plus our constant of integration. Okay, now that's our antiderivative now. In terms of u, let's convert this back in terms of x. So this becomes 2/3. U is equal to this, so it'll be 1. So this becomes 1 plus the square root of 3x. Let's see, minus the natural log absolute value of 1 plus the square root of 3x plus c. And there you've got it. Also, see, this one thing we could do, well, I can just leave it like this. Will be in brackets here. So I just leave all this multiplied by 2/3, so that'll work okay. You can multiply 2/3 inside in parentheses. It'll be 2/3 times 1 plus the square root of 3x minus 2/3 natural log absolute value 1 plus the square root of 3x plus c. So you can distribute this inside your parentheses here. This is what it would look like. Okay, now that was a pretty good problem. Like I said, sometimes if you're stuck with an extra variable like this, like I said, go back up to the original substitution and then see if you can eliminate. In this case, we didn't have to solve it all the way for x. Right, so we just had to get rid of the square root of 3x. So just by subtracting 1 from both sides there, we isolated the square root of 3x, and that began our substitution. Okay, I said I want to finish up with one more problem. Let's try a differential equation. All right, and let's try see if we can solve a differential equation. Okay, erase this. So one more problem. Okay, so one more problem. This is problem number 15. And once again, if you're still watching, I appreciate you following me to the end here. Let's take, so with the differential equation, let's take dy over dx equals, and we'll try natural log x over x. And we're going to see if we can solve this at the point, so we'll give us a point on the original graph, so 1 and -2. Now my students, we've done several differential equations, or not a lot of them, but we've done enough that we pretty much know what we got to do. Now we're going to find first of all our general solution, and then we're going to find our particular solution. We're going to find the equation of the original graph passing through the point 1, -2. That is, we're going to solve for c. We're going to find the constant of integration here. So let's get started. Let's multiply dx to both sides. We end up here with dy equals natural log x over x dx, and then we're going to integrate both sides. Now the antiderivative of dy is y. Now as you take the antiderivative of natural log x over x, see, I know that the derivative of natural log x is 1 over x, so we're going to use u substitution and say u equal natural log x. So du equals 1 over x dx. So remember, the derivative of natural log x is 1 over x. Let's multiply x to both sides, so multiply x here, so x du equals dx. So let's make our substitution here. This will be the integral u over x times x du. Now the x's are going to cancel out. And we have y equals the integral u du. Now u du is not a natural log. So that's not a natural log. But we can go ahead and get our antiderivative, right? So the antiderivative would be y equals, this would be u squared over 2 plus c. Now I'm going to put this back in terms of x. So we end up here with y equals 1/2. So 1/2, this would be, u is all squared here. So it would be 1/2 natural log x to the second power. So remember, u equals natural log x, okay, plus our constant of integration. All right. Now remember, this is called our general solution. All right, so we found our antiderivative in terms of x, y, and c. Now to get our particular solution, we have to solve for c now. To solve for c, let's go back up to our original information here. We're given the point 1, -2. And let's see what we get. Substituting 2 in for y, -2 in for y. So we have -2 equals 1/2 times natural log, substituting 1 in for x squared plus c. Now remember, natural log 1, if you remember from the beginning of the video, natural log 1 is 0, right? So 0, so -2 equals 1/2 times 0 squared plus c, or -2 equals c. So that's going to be our cost of integration. Now let's go ahead and write our solution now. So our particular solution will be, y equals 1/2 quantity natural log x to the second power minus 2. So c is -2, so minus 2. This is going to be our particular solution now. All right. Okay, hopefully we did a bunch of examples, so hopefully by now you have a good idea as to how to do some of these natural log problems, right? So some of these integrals, you're looking for these fractions, it's all basically u substitution for the most part. It's going to be u substitution. So hopefully now, I think we are ready to get started on our homework. There we go.